Hey! Hey! I'm Mr. O, here with another moment at the Children's Museum of Houston.
Oh, check out the wings on this butterfly.
Oh wow, they seem to shimmer in the light.
Did someone say, oh wow?
That was me. We were just looking at this butterfly's wings.
Ah yes, the blue morpho butterfly with the iridescent wings.
Irritated what?
Iridescent. That means that the colors seem to change slightly depending on the angle that the light hits it. It makes it sort of shimmer.
So, what makes the wings iridescent?
Well, the wings have nanostructures that create interference patterns by reflecting the incident light through successive layers. Let's try that again. Most butterflies' color is caused by pigments. That's a substance that holds an actual color, like paint or crayons. So with this buttercup butterfly, no matter how I hold it, you always see yellow. In the case of the blue morpho butterfly, the undersides of its wings are pigmented, as you can see, but the tops are clear. Even though it looks blue, if we hold it up to the lights like this, you can see the colors from the underside of the wings. So the blue iridescent color is not caused by a pigment, but rather the way the light interacts with the structures on the wing. Let's look closely at a blue morpho butterfly wing. When observed at the macro scale, that's what we can see with just our eyes or hand lens, it looks solid. As we zoom in closer, we reach the micro scale. That's where we need to use a light microscope to see the wing structures. Notice that the wings consist of rows of scales. As we zoom in even closer, we shift to the nanoscale. That's where we need to use special tools like scanning electron microscopes to see the structures. Here we can see the scales actually have very, very tiny gaps in them. These nanostructures in the wing are the key to the blue color. You may recall from a prior oh wow moment, we said that the white light, the light we normally see with, is actually made up of lots of different colors: red, orange, yellow, green, blue, indigo, and violet. When light enters the nanostructures, it reflects or bounces around and around. All this bouncing cancels out some of the colors that make up white light, eventually leaving only the iridescent blue color that we see. To further illustrate how it's nanostructures that cause the iridescence, we're going to make the color change. This is alcohol. When I put a drop on the buttercup butterfly, the color doesn't change because it's a pigment. But when I put a drop on the blue morpho butterfly, the color changes to green. The alcohol fills in the air gaps on the wings, so now all the colors in the white light are canceled except for green. As the alcohol evaporates and the wing dries, the normal iridescent properties of the wing return and the color changes back to blue. Let me show it to you a different way. Before we begin, remember, science is fun, but it can also be dangerous, so always have a responsible adult helping you.
We are going to create iridescent thin films.
For this you'll need a large container like a plastic shoebox with water, clear nail polish, and some pieces of black paper that fit in the container.
First, submerge a piece of paper in the water. Next, drop 1 to 2 drops of clear nail polish onto the surface of the water. Finally, carefully lift the piece of paper out of the water, making sure to pick up the thin film floating on top. As you move the paper around, you'll see colors appear all over the surface. The iridescent surface is created by the thin film.
But why does the film create different colors?
Nail polish is oil-based and so floats on top of the water. Since you aren't dropping that much in, it spreads out very thin over the surface. So thin it's only a few hundred nanometers thick. That's about the same thickness as the outside of a soap bubble. However, the film is not uniform. The thickness varies along it. As light passes through the film, it has to travel different distances through it before bouncing back, and as a result, only some of the color reflects back. So the different thicknesses create different colors because of how far the light has to travel through the film.
You said these films are similar to bubbles in thickness. So is that the same reason we see lots of colors in bubbles?
Yes, the colors in bubbles are due to the bubble film being different thicknesses. In other words, your bubbles are also colorful due to iridescence.
So this is fun and interesting, but what's the big deal?
Well, both the butterfly wing and the thin films clearly demonstrate how structures at the nanoscale, whether it be the scales on a butterfly wing or the thickness of a film, can affect how things behave at the macro scale. And scientists and engineers can affect things at the nanoscale in order to create all sorts of new products. For example, this is a classic solar panel, hard and rigid, but this is also a solar panel. By taking advantage of properties at the nanoscale, engineers were able to create a panel that's thin and flexible. This sort of technology is already being used to create clothing and bags that can recharge portable electronics just by taking a walk outside. Now this isn't quite the same thing as making iridescent films, as we want this to be all the same thickness, but it is thin films that give this panel its flexibility. So structures at the nanoscale affect properties at the macro scale, once again proving that small things can have a big impact.
This has been another oh wow moment from the Children's Museum of Houston. We hope your mind can come out to play.